Hello and welcome. Today we're going to look at Charged Particles, Chapter 27, Part 3. Specifically in this presentation, we're going to focus on the Hall effect. As you can remember, we use a metal plate for the Hall effect. We make a current flow through it, and then we bring a magnetic field closer to that plate, which deflects the electrons to the one side, what we've now learned with our Bill force. So that creates a negative side on the one plate and a positive side on the other plate. And we can measure the voltage there, and that would be a way to measure the size of the magnetic field strength, and we use a Hall probe to do so. So in this presentation, it's very important that you know that we're going to speak about the thickness, okay, and we're going to speak about the distance from the positive side to the negative side. So think of it as a parallel plate. There's the negative, there's the positive, okay, and we're going to use that distance across from the left to the right there to determine that over there. So first things first, we know that there is an electric field created, and the formula for an electric field is E is equal to V over D, where we have the voltage, the potential difference between them. We're going to call that the Hall voltage, and that is the thickness or the distance between the positive and the negative side, as we've explained. So that side is the negative, that side is the positive, and we're looking at that width, if you want to call it that, of the metal piece. Okay, so that's the first equation that we're going to look at. Now remember, as we've just discussed, when this happens, we have our electric field force equal to our magnetic field force, which we've discussed, similar to electron selection. And in here we can see the velocity at which the electrons are flowing. Okay, we know the charges, so we can make it capital Q. Okay, and this tells us that the electrostatic force and the magnetic force at that point is equal. Okay, so if we bring that into place here, we're going to end up with the Hall voltage over the distance times the charge. This is still the electric field part, is equal to the magnetic field, the charge, and the voltage. Okay, so remember, what is not the voltage, the velocity. So there's voltage, here's velocity, and if we're looking at this, we're looking at the flow of electrons, and what we've learned in AS, we've learned about this formula which speaks about current, okay, and we have NAQV, and that V was the mean drift velocity. So this is the drift speed, or how fast they go through. So V is I over NAQ. But before we go further with A, the area that we're talking about is once again the thickness and the distance. Okay, so when we're calculating the area, we're looking at the thickness and the distance. Okay, so we substitute that in there, and we substitute that in this space, and we end up with the following formula. In the space of the V, we write now our I, our N, our Q, so that can be a capital Q, and our thickness and the distance there. Okay, and if we start cancelling out everything that is similar, we find the following. The charge cancels with the charge, the distance cancels with the distance, and if we rearrange everything, we find that the Hall voltage is equal to the magnetic field strength, the current, and then at the bottom the number density, which depends on the type of metal we're using, the thickness of the metal, and also the charge of the charges that we're using, mostly electrons if we're using a electric current. Now it's also important to remember with our current flowing through, so here's my wire, we create a positive and a negative side, but we also have a magnetic field going through, okay, well, let's just put it next to, through that. So we are creating once again a electric field and a magnetic field which is perpendicular to each other. And as the current flows here, the velocity that we spoke about, okay, we now have these two forces being equal. We have the magnetic field, okay, which has a magnetic force, and we have the electrostatic field, and they have an effect on these current. And as the current flows through there, we get to that point of equilibrium, and then they travel in a straight line. So if we look at our equation for the Hall effect, we can see that the magnetic field, the current, and the charge has an influence, and by rearranging this we can calculate, if we know the voltage, because we can measure the potential difference, we can measure the size of the current with the ammeter, we know the charge and we can physically measure the thickness, and the number density depends on a material, so if you know what material you're using you can get that. We can go and calculate the magnetic field, and that's exactly how a Hall probe measures the magnetic field with all of these quantities that it has. So it has already it knows which material it's made of and the thickness, because that's part of the probe, and that's electrons, so it just takes these two measurements and calculates the magnetic field strength. So one of the applications of a Hall probe or a Hall sensor is something like this. Now it doesn't completely fill into what we're doing, but in a factory they can calculate the distance between things, and they can calculate the movement. So like here is a gear that's moving, and they can calculate by using the different gaps. So we've got a Hall probe and a magnetic field, and using the voltage that runs through it, they can calculate the distances, which creates something which shows them that the wheel is still working, that all the teeth is still the same, not broken. And so this is just a practical application, much more complicated, but we use Hall probes and Hall sensors in a lot of other everyday applications. I hope that doesn't leave you with too many questions. Please go and finish all the other work in your pink booklet, and then yeah, I believe that you'll be able to succeed in this chapter. Thank you. Have a nice day.